Hello, and welcome to the lecture on the topic of uniform and non-uniform circular motion. Okay, of course, we're going to define what uniform and non-uniform motion mean, but maybe it's obvious that we're going to be talking about objects or particles moving in circular paths. Now, let's have some context here. We're discussing this topic of circular motion in the chapter where we're covering the introduction to acceleration and velocity vectors. This is also the same chapter where we introduce projectile motion as one very important, very applicable, very real-life example of a two-dimensional kinematic problem where there was a constant acceleration and that drove a certain type of parabolic path of the projectile's trajectory. Now, why talk about circular motion? Because it's the other very common, very important, very applicable type of motion that involves constant acceleration. But, it's not really constant acceleration, okay? It is constant acceleration in magnitude if the motion is uniform. I'll define that in just a minute. But then if it's non-uniform, then there's nothing constant about the acceleration, all right? So definitely this is a step up in complexity in terms of projectile motion, where we could just really count on the acceleration just pointing down and being gravity. Unless, of course, it was a rocket, in which case it wasn't quite a projectile, but it behaved similar to a projectile, okay? Or we could say it was a projectile in the y direction, but not in the x direction. But not to get off topic, what the heck is going on with circular motion, all right? Well, circular motion has some key ideas, some key vectors that are very representative of the system. So it really is the other common type of motion, okay? So let's define the kinematics, define the terms, and do some examples. All right, so we have quite a few key terms here. All right, so key term number one, uniform circular motion. What is it? What do we mean by uniform, right? What's uniform about it? Well, it means moving in a circle at constant speed. So the uniform part means that the speed is constant. That's actually the kind of the physical definition of this word here. Uniform is constant speed, right? You have to think of that code. All right, you might think, because uniform could mean, oh, the circle is an oblong or something, right? But it doesn't, right? And by the way, all of our circles are circles. We're not talking about any path that's like an ellipse or any other shape. This is strictly circular motion. That part doesn't vary, okay? So now we've got the uniform circular motion, which is constant speed circular motion, all right? But the velocity is still non-constant. Why would the speed be constant but the velocity be non-constant? Well, think about a circular path. As you're going around that circular path, your velocity vector is constantly changing where it points. And since velocity is a vector, it's defined by not just its magnitude, but also its direction, all right? So uniform circular motion, constant speed, non-constant velocity. Constant magnitude of velocity, but not constant direction of velocity, all right? Okay. This type of circular motion has only something called centripetal acceleration. It only has one form of acceleration, and it's called centripetal acceleration. I'll define it in just a second. Okay? Now, what about non-uniform? Well, I bet you could guess. It's moving in a circle while slowing or speeding up. So it's simply where your speed is not constant. So the speed is non-constant as well as the velocity. Okay? So it'd be like going in a circle, having a velocity vector, having a smaller velocity vector, smaller still. This would be like slowing down, right? That would be non-uniform circular motion with a slowing or speeding up while turning. Still a perfect circle, but slowing or speeding up while turning, okay? This type of circular motion has two components of acceleration. And of course, we'll talk about those because our next two key terms mention two different types of acceleration, all right? Well, those are going to be them, all right? And they're the radial and centripetal forms of acceleration. Radial, centripetal, right? So it almost seems like I've mentioned three types of acceleration, but let's clarify that, all right? So centripetal, otherwise known as radial acceleration, is acceleration that points towards the center of the circle. In fact, the name centripetal means center seeking. So it is a form of acceleration that points directly towards the center of the circle. All right? Centripetal and radial are synonyms. Those terms are absolutely interchangeable. I will generally use radial when I talk about accelerations. If I'm talking about forces in later chapters, I might use centripetal. So it just depends on the context, but they're absolutely synonyms. Okay, this acceleration vector is constant in magnitude, but not direction for uniform circular motion. okay? So it will always have the same length for uniform circular motion. So in other words, for uniform circular motion where the velocity vector is constant in magnitude, so is the centripetal acceleration vector. And we learned up above that for uniform circular motion, the only type of acceleration there is centripetal. So you can see why uniform circular motion is such a simple, elegant type of motion that it would be kind of lumped in the same chapter as projectile motion, which has a kind of a similar set of real like kind of refined idea there, right? Not a messy system, not a bunch of complicated vectors, but a very, very specific type of motion, okay? But at the same time, we are simultaneously talking about non-uniform. So I want to have that ability to think about these two ideas distinctly, and I'll obviously show you examples of both. But let's carry on with our definitions, our key terms. What is tangential acceleration? Well, that is acceleration that points tangent to the circle's path, as opposed to in the direction of the radius, it points in the direction of the velocity, okay? And you'll see a picture of that, okay? Tangential acceleration creates changes in speed during non-uniform circular motion, okay? So uniform circular motion doesn't have tangential acceleration. Tangential acceleration creates non-uniform circular motion. It creates changes in speed, the slowing down or speeding up, okay? That should all make sense. Tangential acceleration is perpendicular to the radial acceleration by definition, okay? And the tangential and radial directions form coordinate axes, okay? So we actually have a coordinate system now that isn't x and y, but is tangential and radial. Now we can compare it to x and y coordinate systems, and I will, because I want to kind of pay a lot of attention to how we think about angles as we move around circles, but the radial and tangential form their own coordinate system, all right? And again, lots of pictures to illustrate that idea as we move to the practice and even on this page in just a moment. All right, another term, the period of revolution, okay? It is the time to complete a circle, all right? A time to complete a complete circle. I don't know if that's a very great sentence, but it's just the time to go all the way around, okay? Periods are constant for uniform circular motion. So if it takes a certain amount of time to go around the circle once, if your speed isn't changing, it'll take the same amount of time to go around the circle the second time. Of course it will, right? Because the same speed, that means the same time to make a full circle over and over again. If you're slowing down or speeding up, that's obviously not the case, okay? And then finally, tangential velocity. That's just velocity. In fact, the only reason I included this key term is just kind of as a reality check to think about what tangential means, right? Tangential means, parallel to the path at a particular moment. It's the tangent line. And velocity, by definition, is tangential. So that means that tangential acceleration is, by definition, parallel or anti-parallel to velocity, okay? All right, here is a figure, right? I'm zooming on this a bit. So what are we looking at here? So we're looking at a circle, and we're looking at this green dot going along a few points as it moves along a little segment of a circular path, okay? I've included this picture to illustrate the ideas we talked about, and let me ask you this. This green dot, is it undergoing uniform or non-uniform circular motion based on the key terms we just introduced? And they're brand new, so it's okay if you don't know, but think about it for a moment, okay? Is this uniform or non-uniform circular motion? Well, maybe the big giveaway, the initial giveaway, is the velocity vectors. If you look at v1, because we could think of this green dot located here as time 1, that v1 is kind of short. As we move forward in time and find the dot in a new position, what's happened with the velocity vector? How does v2 compare in length to v1? It's longer, okay? So that tells us this is non-uniform. If it was uniform circular motion, the v vector would have turned, obviously, as the green dot moved, but it would have remained the same length, okay? So this is non-uniform circular motion. And we can see v3 is longer still. Next thing to notice, the coordinate axes. All right, we have a r and t as a coordinate system at each green dot. All right, that is a coordinate system based on the radial and tangential directions. So that's the interesting thing about the radial tangential coordinate system, is that it is a moving coordinate system. Now, any coordinate system can be a moving coordinate system, but this coordinate system is fixed to the particular location of the particle or object in time. And it always has one axis that points towards the center in the radial direction and one axis that points parallel to velocity in the tangential direction, okay? At the same time, we could have an x and y coordinate system that is fixed to the center of the circle and doesn't move. And then we could obviously compare the two coordinate systems at any particular moment in time, okay? in an angular sense, compare how their axes match up or don't match up, right? All right, next thing to notice, all right, is the acceleration vectors. All right, so what are acceleration vectors? Well, we have, I'll start with the centripetal one, AR, right? Why AR for centripetal? Because radial, right? So this is the radial acceleration vector for V1. This is the radial acceleration vector for V2, and the radial acceleration vector for V3, or at point 3, right, at point 2, however you want to phrase it. Notice that the radial acceleration vector always points towards the center of the circle because that is what it does by definition. But notice that it is growing in length, all right? Why is it growing in length? It's growing in length because this is non-uniform circular motion. Had this been circular motion and every velocity vector had the same length, so too would every radial acceleration vector. How do we know that? From the formula, and I'll show you in just a moment, okay? Now, neither of them, the velocity vector nor the radial acceleration vector for circular motion, would have truly been constant, because although their magnitudes would have been constant, they would have both been constantly changing in direction, okay? But here, they're changing in both direction and magnitude, all right? And why are they changing in magnitude? Because of this other acceleration, a sub t, right? So this vector is the tangential acceleration. And here I just drew it as the same, approximately the same length each time to represent that the particle, the green dot, was speeding up at a steady rate, okay? So if it's speeding up at a steady rate, then the tangential acceleration vector could be constant in magnitude, but it like all these vectors, is always changing its direction. So it's kind of interesting, right, that even when we have things that are constant in circular motion, they're never more than just constant in magnitude. Nothing remains constant in direction. And so kind of right away, there's a little telltale sign here. And it's telling us that circular motion is inherently, fundamentally more complex than projectile motion. It just has extra considerations. You can't turn in a circle, you can't revolve around and not have extra math, extra geometry, extra trigonometry, okay? And I bring that up because when we really dig more into our chapters on rotation and the dynamics of rotation, you'll see that is everything that happens in rotation is very similar to things that happen in translation, but they're more complex. Okay? All right. So that little kind of warning or foreshadowing things to come, we got one last acceleration vector shown in this figure, and that's just A. A is the total acceleration. All right? And we can see that it is just composed of, by tip to tail vector addition, of two components, the radial component and the tangential component. All right, I think we're ready for our equations. Okay? So first of all, we have our radial acceleration, also known as the centripetal acceleration. I can write that sometimes as just AC. Here, it's just its magnitude, and its magnitude is v squared over r, okay? Not going to derive it. If you want to see the derivation, look in your textbook, okay? So v squared over r is telling us that if velocity remains constant, so does radial acceleration, because obviously the radius must remain constant. Furthermore, the radial acceleration is proportional to the square of velocity, so it can be quite large, right? Because you're squaring something. Furthermore, in non-uniform circular motion, where v is growing, then the radial acceleration is growing quite rapidly, again because of the square, okay? And that's our magnitude of radial acceleration, all right? V squared over r. All right, next formula. Oh, by the way, I labeled velocity and radius, okay? Just in case you were confused what v and r were, okay? I assume you weren't. And then we have the period of revolution, that's t. Uppercase T represents period, because period is measured in seconds, all right? And so T for time, but we tend to use uppercase T for periods. And it's the period to complete a cycle. In this case, since we're talking about circles, it's a revolution. But period can apply, as we'll see later on, to things like oscillations, like bouncing up and down, right? A lot of similarities between those two phenomena. Furthermore, if we take the reciprocal of period, we get something called frequency. And frequency is just how many revolutions there are per second. If period is how long it takes to make a revolution, then frequency is just how many revolutions there are per time. The basic unit of time is a second, so revolutions per second is frequency. All right, frequency is 1 over t. Okay. All right, now our total acceleration vector, okay, which is just the vector sum of the radial component and the tangential component. Right, here's the tangential acceleration as a vector, and then look at it as a scalar down here. Right. As a scalar, we can see that it is just the instantaneous change in speed. It's just dv or dt, okay? All right, and since it is an instantaneous change in speed, I mean, I could give you like a time-dependent velocity function and then ask you to find the acceleration, the tangential acceleration at a particular time, kind of give you a kinematic equation. Generally, I'm just going to give you a value for a tan, for the tangential acceleration. And then down here, by the way, I know I skipped over it, but I'm going back to it. This is just showing that the total acceleration vector in magnitude is just equal to the Pythagorean sum of the two components, okay? Because it is a right triangle after all. Okay, all right. So that is our background out of the way. Let's get to some practice. Okay, so I grouped our examples into three types. Type 1, simple problems that are uniform circular motion and have calculations of speed, period, and magnitude of centripetal acceleration. Okay, so it's just all about just working with uniform circular motion and doing some algebra with them. All right, mostly plug and chug. Type 2, fairly complex problems that involve uniform circular motion and calculations of centripetal acceleration vectors or average acceleration vectors. So notice the difference between type 1 and type 2 is type 2 mentions vectors, type 1 does not. So type 1 is all about scalar quantities, magnitude. Type 2 will actually have to worry about angles and the actual kind of geometry of the circle. Type 3, complex problems that involve non-uniform circular motion and calculations of total acceleration vectors composed of radial and tangential components. Now, honestly, type 3 isn't inherently more complex. You can kind of make any of these problems, or at least type 2 and type 3, as complex as you want to, depending on what questions you ask. And I'll say, as I was writing up these notes and getting them ready to present for this lecture, I realized there's a lot of geometry of circles involved. We do a lot of angle calculations, a lot of thinking about how one angle points relative to another, okay? So you'll see that, so that's what you have to look forward to in this video. But let's first do some plug and chug with scalar equations dealing with uniform circular motion. All right, example 1. Two children stand on a carousel that is turning at a rate of 0.233 revolutions per second. Okay, revolutions per second, what is that? That's a frequency. How much faster is a child moving that is standing 3.105 meters from the center compared to a child that's standing 0.954 meters from the center? So who's moving faster? The person that's closer to the center or the person that's further away? Because the carousel is one object. The whole thing is completing a revolution simultaneously. So who's moving faster? All right. So the idea is that we have the two kids, right? One is maybe near the edge, right? And then one is closer to the axle of rotation, okay? The axis of rotation, but the actual mechanical axle of the ride, okay? So we're just going to compare the change in velocities, v2 minus v1. All right, so then you can see I'm assuming that v2 is going to be bigger because it will be. v2 has to be bigger because v2, the kid that's further out, is completing a longer path in the same amount of time. So they must be moving faster. The further you are away from the axis of rotation, the faster you go. All right? And so then we're just going to find the two velocities. Velocity is 2 pi r over t. In this case, we have two different r's, so I have r sub 2 and r sub 1. All right? And then I factor out the shared part of this comparison, of this difference, which is 2 pi over t. My t is 4.29 seconds. And then I just plug in my two radii. And so then I find that the difference between their velocities is 3.15 meters per second. And that's because the child that is further out is moving quite a bit faster, right? That's a significant change in velocity, okay? Now, but wait, where did I get this period from? Right? I wasn't given the period, I was given the frequency. Well, I got it from this, all right? So I take a frequency is 1 over period, all right? And so then I was told that there's 0.233 revolutions per second. Okay, well that means that there's about a quarter of a complete revolution per second. That means that this carousel takes more than a second to complete a revolution. So all I do is just take the reciprocal of 1 over 0.233, or rather I take the reciprocal of 0.233, which is 1 over 0.233, and that gives me 4.29. That's the period. Okay, simple as that. Right? Just raise it to the negative 1 power. Okay? All right. So that's it for example 1. Hopefully it makes sense. All right, let's look at example 2. The rotor of an ultracentrifuge rotates at 50,000 RPM. Okay, RPM. You've probably seen that before, right? For lots of different, devices, cars, for example. A particle at the top of a test tube in the centrifuge is 6 centimeters from the axis of rotation. Okay, what is the centripetal acceleration of that particle in g's? All right, so that's g's, like Earth accelerations, common way to measure acceleration. You know, people talk about like g-force, although sometimes that force is a misnomer. Sometimes they're actually talking about the acceleration, but they call it force for some reason. But g's are just, you know, basically multiples of 9.8, okay? All right, so let's think about this. And by the way, I looked this up. These are actual quantities for ultracentrifuges, and that is the name for them. All right, so then we have 2 pi r over t to find the velocity. All right, now, was I given the velocity? No, I was given the frequency again. All right, so then I'm going to rewrite this as 2 pi rf, okay, because that would be another way of expressing velocity. 2 pi, I got my radius, which is 6 centimeters, and then I'm going to convert RPM into revolutions per second, okay, because I want it to be in base units. So if I have 50,000, which is 5 times 10 to the 4, if I divide it by 60, I'll get revolutions per second as opposed to per minute, right, because there's 60 seconds in a minute. And by the way, the units of frequency, inverse seconds, are also called hertz, all right? So hertz are units of frequency. Hertz are seconds raised to the negative 1 power, or hertz are just 1 over time, 1 over seconds, okay? And that gives me a velocity of 314 meters per second. Okay, that's fast. Yeah, that's really fast. You know, that's almost the speed of sound fast, which is actually pretty remarkable if you think about that. These things actually exist in biological laboratories. Okay, and here's the thing: it's going to lead to a lot of acceleration. Let's see how much. All right, because if this seems like a big number, and it is, right? It's, you know, it is just literally 20 meters slower than the speed of sound, 20 meters per second slower. But the acceleration that we're going to get is mind-boggling. All right, so let's find the centripetal acceleration, v squared over r. All right, so I just take that velocity and I square it and I divide it by our radius, okay, and I get 1.64 million meters per second squared. Okay, and then I want it in g's though, so I just divide that by 9.8 because then it'll just be multiples of Earth gravitational acceleration, and I get 168,000 g's. And I wrote it in non-scientific notation to kind of make it, you know, more dramatic. All right. So 168,000 Gs. That's how fast these ultracentrifuges go. Why do they go that fast? So they can tear apart molecules. Essentially in biology, there's 2 ways to tear apart molecules. Giant magnets, the biggest magnets in the world at, like, you know, 10 Teslas, or the fastest centrifuges. Okay? All right, tearing apart biological molecules like proteins and so on. Okay? Amino acid chains. All right, example 3. Based on the radius of the Earth, being 6,360 kilometers, so a good approximation of the radius of the Earth, what is your velocity when you are at the equator? Okay, we can calculate that. You know, definitely the Earth is uniform circular motion. What is your centripetal acceleration when you're at the equator? That's kind of cool, right? And what are these values at the North Pole? Okay, so at the equator, we're just going to do 2 pi r over t. All right, so 2 pi, plug in our radius, make sure to convert it to meters by multiplying by 1,000, and then take the period, which is 24 hours, multiplied by 3,600, because that's how many seconds there are on an hour, just 60 squared. And so there it is. There is our velocity when you are at the equator, 463 meters per second. That's pretty fast, right? But that's really fast. It's faster than the speed of sound. How do we not notice that people at the equator are moving at such incredibly fast speeds? Well, think about what would be the manifestation of that incredibly fast speed. It'd be acceleration, right? That's what you would feel. You'd feel the acceleration. Because otherwise your velocity is constant in magnitude. So you'd only experience the only sensation you experience would be the centripetal acceleration. All right, and let's find out how big is that centripetal acceleration. Is it going to be, you know, huge? Well, probably not, because people on the equator don't complain about like lifting off the ground or being smashed into the ground or something, right? And you'd be lifting off the ground. Well, let's find it. All right, let's find the centripetal acceleration. That is, it's v squared over r. All right, so we're going to square 463, big number, but unlike before, we're dividing by just a few centimeters. We're going to divide by the entire radius of the Earth. All right, some 6 million meters, right? Because if it's 6,000 kilometers, that's 6 million meters. Okay, and we end up with this rather small acceleration, 0.034 meters per second squared. All right, just a small fraction of the actual gravitational acceleration. You think about this, this is less than 1% of gravitational acceleration. So it's actually not a big deal, okay? The centripetal acceleration of people on the equator is, although measurable, because it's 0.3% of gravitational acceleration, it's still very small, okay? All right. What about on the North Pole? Just all zero. People on the North Pole don't have centripetal acceleration because they're not moving. All right. So if you're at the North Pole, you'd actually weigh a little bit more than at the equator. Okay, a measurable amount, but again, 0.3% difference. Okay, and the 0.3% I keep mentioning is just taking this, right, and dividing it by 9.8 and multiplying by 100. Okay, it gives you 0.3%. Okay, all right. So North Pole, no motion, thus no velocity, thus no acceleration. Okay, centripetal acceleration. Cool. All right. So now our first problem that involves velocity vectors. Okay, a cat rides a merry-go-round, turning with uniform circular motion. Okay, well, of course, cat on the merry-go-round. At time t1, which is defined as 2 seconds, the cat's velocity is given as this vector here, right? And I'll draw this so it'll make more sense. Measured on a horizontal xy coordinate system with its origin at the center of the ride, okay? At the center of the circle. At t2, which is at 5 seconds, so 3 seconds later, right? Because notice t2 is at 5 and t1 is at 2, so the difference is 3 seconds. The cat's velocity is given by these vectors, okay? And notice that this vector here is really similar to the initial velocity vector. It just has a negative on both the I hat and j hat, all right? So in question A, what is the magnitude of the cat's centripetal acceleration? Okay, good place to start, but we need to draw the picture. So this is uniform circular motion, okay? So we know what we're getting into. There's going to be no tangential acceleration, no tangential component. And here's our picture. Zoom in on this. All right, here is the circle that the cat is going to take. Here is the point at t1, right? See, that's a 1. And here's the point at t2, okay? The time to go from this point to this point is 3 seconds, okay? There's the initial velocity vector. There is the second velocity vector, or velocity vector 1, velocity vector 2, okay? Here is the only acceleration acting on the cat at point 1, which is centripetal acceleration pointing towards the center. And here's the only acceleration acting on the cat at point 2, again, centripetal acceleration pointing towards the center. All right? So, what are we looking at then? Right? Well, why do I even know that V1 points in this direction? And why did I know to draw it on this part of the circle? Well, there's an interpretation going on here, right? Or just, following the details. My initial velocity vector is positive in both I and j. That means it must point up and to the right based on my chosen coordinate system, okay? And we were told to use this coordinate system, okay? A standard xy coordinate system located at the center of the circle. Well, if my velocity vector points positive in both, right, then it has to point this way, but yet at the same time it has to be tangent. That means I can't put this velocity vector anywhere else, right? It has to be located right there, okay? Make sense? Likewise for velocity vector 2, I know that since it has a negative component of y and a negative component of x, it has to point down and to the left, which means it has to be located right there, because that's the only place you can have a vector that points down to the left and be tangent to the curve of the circle, right, at that point. Okay, so hopefully that makes sense. Okay, so then let's get into actually solving part A, and then we'll just kind of carry on from there. Okay, so first of all, we know that the radial acceleration is v squared over r. All right, and we know that v is a constant. All right, and we see that the period of the revolution is 6 seconds. Wait, where did that come from? Well, think about it. I know that these two velocity vectors are exactly 180 degrees apart. Why do I know that? Well, because they point anti-parallel to each other. Look at that. They have the same magnitude I and j, just one has a negative. So I know that this is 180 degrees. Okay, you can quickly reason that out. If that's 180 degrees and it took 3 seconds, 5 minus 2, then it would take another 3 seconds to complete the circle, which tells me my period is 6. Okay? All right? So no math there, just kind of interpreting. A little bit of math, right? But mostly just interpreting the data you were given. All right? And then we can use this to find the radius. Because notice we're not given the radius of the ride, but we have enough information to find it. Okay? So we know that v equals 2 pi r over t. We know t, and we know v. So we can actually solve for the radius because there's only one radius that would work, okay? And again, this is assuming that the cat's on the edge of the ride, right? So it's really more of the radius of the cat's path, but we'll assume it's the radius of the ride, okay? So we're going ahead and solve for r. V is going to be found through the Pythagorean theorem based on the two components we were given, all right? There's our period, there's our 2 pi, all right? And we end up finding that the radius of the ride is 4.77 meters. which turns out to be a really big ride, right? Well, reason, like 15 feet, like, why 15 feet radius? Yeah, it's pretty big, right? But maybe believable for a big carousel. Anyway, all right. So then we can find the centripetal acceleration, otherwise known as the radial acceleration, because we needed r, right? That was a missing piece. So then we just plug in our 5 meters per second squared. Wait, how do I know it's 5? Oh, well, because this is a 3, 4, 5 triangle. I could have just written this square root as 5, okay? Right? Because, 9 plus 16 is 25. Take the square root of 25, you get 5, okay? So 5 squared over the radius we solved for, and we end up with 5.24 meters per second squared. It's a pretty significant acceleration here, right? It's almost like a g, right? Well, at least half a g, okay? All right, so moving right along, let's go to part B. Let's first see what they're asking for in part B, what I'm asking for. What is the magnitude of the cat's average acceleration during the time interval t2 to t1? Okay, so what is that, or is t2 minus t1, okay? So what is that, the average acceleration? Average acceleration, we never talked about that, but we know what to expect, right? We know acceleration is a vector. We know how to deal with averages. So we should be able to figure out what the average acceleration vector is, okay? Right? Because I do ask for the average acceleration vector, not the magnitude of the average acceleration, okay? Well, it's just this. So here it is, the average acceleration vector. Notice I have the bar to denote an average and the vector symbol to denote a vector. It's just the change in the velocity vector over the change in time. So it's just v2 vector minus v1 vector over delta t, okay? We expand that out. We put in v2 with its appropriate components on I hat and j hat, subtract v1 as a vector, divide the whole thing by 3. Obviously, this is going to remain a vector. I'm going to combine all my terms, so everything that's attached to I hat and j hat, right? When I combine terms, I get negative 6 I hat and negative 8 j hat, but then divided by 3. So then it ends up being negative 2 I hat, negative 2.67 j hat with units of meters per second squared. And there it is drawn right there, okay? So it doesn't have the same magnitude as the centripetal acceleration. It doesn't necessarily have to by any means, right? But it's, but I kind of drew it as a similar magnitude, all right? If we were to think about its magnitude, what would it be, right? 2 squared plus, almost 3 squared inside the square root. So, you can kind of think about what its value would be. It would be less, right? Because both of those are less than 3 and 4. So it would have a shorter magnitude, okay? But its direction is well defined. And we'll see that its direction is very related to the instantaneous centripetal acceleration vectors because it's exactly halfway in between. Why is it exactly halfway in between? Because the whole uniform circular part, all right? Uniform circular motion part, that is. Okay, but anyway, we found the vector by just, simply doing an average, okay? But I know we haven't done an average of vectors before, so make sure this makes sense to you, okay? So now, I think that was it for part B. Yeah, so now on to part C. What angle does the average acceleration vector found in part B make with the negative x-axis? All right, so that's why I've drawn the average acceleration vector. So here I just kind of put it halfway between A1 and A2 because since it is the average, it kind of made sense to put it there. But notice I also duplicated it down here at the origin. I did that so I could clearly show the vector theta, which is the vector we're being asked for in part C. The vector between the average acceleration vector and the negative x-axis is theta. All right, let's solve it, okay? Oh, by the way, here's the magnitude of the average acceleration vector, okay? All right, 3.33. Yeah. It's shorter than the magnitude of the radial acceleration vector. All right, so we can see from the figure above that the A average vector is in the third quadrant. Okay, clearly is, okay, because it has negative j hat components and negative I hat components. Okay, so that means we can find theta by just considering that tangent theta is just going to be A average y over A average x. It's just opposite over adjacent, right? The vertical is the opposite of theta, and the horizontal is the parallel, or the adjacent of theta, okay? So then if we isolate theta, it's just going to be tangent inverse of 2.67, which is the y component, okay, over 2. And I only care about their magnitudes because I'm measuring the angle relative to the negative axis, okay? And it's 53.13 degrees. Excellent, all right? There we go. We found theta. Now here's the interesting thing. That theta must be the same theta as v1, as the tangent inverse of v1y over v1x. Okay? So you can prove that to yourself, but that must be the same theta, or just plug in the numbers that you were given for velocity. Okay? But they are the same angles. Okay? And then part D is going to kind of drive that idea home. What is the angle between the centripetal acceleration at A1, so that one there, and the average acceleration vector that we just found? So in other words, we want the angle between this vector, which I'm duplicating here, and this one here. So what's this angle? Okay? What do you think it is? Are you thinking it's 90 degrees? Let's see. Okay, let's position this here. Okay? So we see that A1 is in the second quadrant. And we can find its angle by considering the figure detail below. So I've just taken a part of the other figure and zoomed in on it. Okay? So we have A1, which I've duplicated starting at the origin. All right? Or actually, I actually left A1 over by the velocity vector to just show where it is. And instead, I duplicated A average vector and put it so it meets up, that its tail touches the tail of the A1 vector, the radial vector at time 1. Okay? And then this is the vector that we're solving for, beta. What vectors do we know? Well, we know theta already. We know that's 53.13. And so we really just want to find this phi vector. Okay? And we know that this is 90 degrees right here. It must be 90 degrees because by definition, velocity being tangent is perpendicular to radial acceleration. Absolutely, by definition. Okay? All right, so then we can find phi by taking 180. This is the 180. It's right here. Okay? Minus 90, that 90, minus theta. Okay? And we know theta already is 53.13. All right? And we could, again, find that by just doing tangent inverse of the components of velocity. All right? Or by using geometry to know that it must be the same theta that we found for average acceleration. All right? And therefore, beta is just going to be theta plus phi, which is going to be 53.13. Oh, by the way, turned out that phi was 36.87. And then beta is just, as I said, theta plus phi. Okay, lots of Greek letters. 53.13 plus 36.87, it is in fact 90. It has to be 90. Okay, but we confirmed it. The result you may have expected. Okay? All right, let's do a couple more problems with vectors and some geometry. So a circular space station has a radius of 1 kilometer and simulates Earth's gravitational acceleration in magnitude along the outer rim of the station. Set in coordinate systems so that the origin is at the center of the station and a person is located at r equals 1 kilometer in the i-hat direction and 0 kilometers in the j-hat direction. So in other words, they're along the x-axis at time 0. Question A, what is the velocity vector experienced by this person at t equals 0? Okay, let's see. So here's the picture, right? Here's that initial position vector, which I'm calling R1, since it is along the radius, okay? I'm using uppercase R to denote just the magnitude of the radius, right? Here is the velocity vector at that point, and I'm calling it 1. I guess I could have called it not, because it is, after all, at t equals 0 seconds, but it's the first thing we're measuring, so it's 1, okay? And, again, these have to be perpendicular to each other, and we just want to find this velocity vector, that's all. Now we can see that we definitely expect this velocity vector to have only a j-hat component. It should point straight up. Okay, so let's see. So here's our 1 kilometer radius. Okay, we know that the centripetal acceleration needs to be 9.81 because it's meant to simulate Earth gravity. I don't know if I don't specify 9.81. I'm not sure why I didn't use 9.80, but here I use 9.81. Okay, and then I'm going to go on and solve for the magnitude of velocity. That's kind of the whole purpose of this expression here. Okay. And I've converted the kilometers to 1,000 meters. And so the magnitude of my velocity is 99 meters per second. So someone on the outer rim of the space station is moving at 99 meters per second. Okay, so then that means that velocity vector 1 must just be 0 in the i-hat direction and 99 meters per second in the j-hat. Okay, and again, we know that because it's got to be perpendicular to something that points exactly along the x-axis. Okay, so v1 is parallel to the y-axis. Okay, we're done for part A. So what do we want for part B? So part B says, what is the velocity vector experienced by this person 35 seconds later? Okay, well, that's interesting, right? So how do we figure that out? 35 seconds later, I mean, well, how far have they moved in 35 seconds? Well, let's see. So the full period of revolution for the space station is 2 pi r divided by the velocity, okay, which ends up being 63 seconds. So it takes someone on the outer rim of the space station 63 seconds to go all the way around. Well, 35 is a little bit more than half of that, right? So after 35 seconds, they made 0.55 of a full revolution, okay? So just a little bit over half of a full revolution. And that's what I've drawn here, okay? Now, that means we can find theta by just taking a ratio, right? So 0.55 of a revolution over one full revolution is the same as some angle theta over the degrees in a full revolution, so over 360. So that means that theta is 198 degrees, just a little bit over 180, which would be a half revolution. Okay, great. So now we know where they're positioned. That's important because once we know where they're positioned, then we can think about this velocity vector. Because here's the velocity vector at the position that corresponds to 198 degrees. Okay? And I drew it here initially tangent, because that's where they're actually located. But then I duplicated that velocity vector over to the origin where I could more clearly see the angles that I care about. Because I'm asked for the, let's see, so what is the velocity vector experienced by this person? Yeah, so I'm asked for it as a vector. Since it's asked, I'm not looking for its magnitude, obviously. If I want to write this as a vector, I need both its components. If I want both the components of V2, then I need some angle. I need this angle here, which I call phi. Okay? So let's find phi. Okay? Okay? So we can see from the figure that phi is 360 minus 198 minus 90, so it must be 71. How do I reason that out? Well, 360 is just the full circle, okay? I know this one right here is the 198. I know that this is 90. Why do I know it's 90? Well, because this is, that's the radius vector. Velocity is tangential by definition, so that must be 90. So the only thing that's left for phi is that 71 degrees, okay? All right, so then I can just say then that V2 is the magnitude of velocity times cosine of 71 in the I hat direction, positive, and then I know it points down in the j hat direction or the y direction, so it's a minus 99 meters per second times sine of 71, and now I actually solve it. It turns out to be 32 meters per second I hat minus 94 meters per second j hat. There we go, okay? There's our instantaneous velocity vector after 35 seconds of spinning. Okay, cool. All right, so let's do something similar for a non-constant acceleration. This is the only problem here where we're actually dealing with a radial acceleration. So not many. We'll have plenty of opportunities in future chapters to do a lot of problems with radial accelerations. So it's not a main focus now. It's just something you need to kind of be introduced to. All right. So a car enters a circular turn of radius 145 meters at high speed and is forced to decelerate at a rate of 1.43 meters per second squared. At that moment, the car is located at r equals negative root 2 over 2r plus root 2 over 2r. Okay, and that's supposed to be this vector right here. Relative to the center of the circle shown. It has a speed of 25.93 meters per second at that moment. Okay, what angle does the total horizontal acceleration vector of the car make with the positive x-axis? So let me draw the vectors and angles we care about. Okay, I know it looks like a lot going on, but there's going to be a radial acceleration. There's going to be a tangential acceleration that points backwards because the car is slowing. That's going to create a total acceleration that's going to point down in a pretty steep angle. Then there's going to be some angle theta that's going to be measured between the total acceleration vector and the r direction. And then if we want to find what we're asked for, because we're asked for the angle that the total horizontal acceleration, or the angle that the total acceleration makes with the positive x-axis. So we're asked to find this alpha value. Okay, so let's go through it. All right, so start by finding the total acceleration vector from its components. Okay, so, well, its radial component is going to be v squared over r, which is going to be 4.637 meters per second squared, and its tangential component was given, right, because it's decelerating at a steady rate of 1.43, right? And so then we can find theta, that's that theta right there, shown in the figure, with simply doing an inverse tangent. It ends up being 17.14 degrees. It's a small angle because most of the acceleration is radial. Okay? All right. Then we can go ahead and realize that the angle that r makes with the positive y-axis, which I call phi, is 45 degrees. But of course it is, right? Because it's equal, it's equal length sides. Okay? And the problem here is I didn't really draw it so it looks like 45 degrees. So bear with me. I extended r down into the fourth quadrant and made it look a bit more like 45 degrees. So my figure is a bit more to scale. Okay, and at this point it's just comparing angles, doing some geometry. We know that beta is also 45 because beta is just 90 minus theta. That's that angle that I drew in there. Okay, because this is the 90. Theta is this, or phi, excuse me. Phi is the angle between the red line and the negative y-axis, so it would be this angle. Okay, because we can see this angle must be equal to that angle. right? Theta and phi are not the same. You can see they're close to the same, but I made sure to include a gap between them. So anyway, beta is 45 degrees as well. So then the angle we want between the total acceleration vector and the x-axis is alpha, which is just beta plus theta, which is 62.14 degrees. Okay, so just geometry of circles here. Really the only physics was finding the radial acceleration and realizing what the tangential acceleration was. Okay, all right. Well, that's it for this lecture of introducing uniform and non-uniform circular motion in our chapter on 2D kinematics. Okay, well, thank you so much for watching. I look forward to talking to you all soon and seeing what questions and ideas come up.